So good afternoon and welcome to the Jones Seminar Series. It's my pleasure to introduce Dr. Erin Baker. She is a professor of industrial engineering and operations research at University of Massachusetts Amherst and the faculty director of the Energy Transitions Institute, which is focused on stakeholder engaged research at the intersection of energy and technology. Dr. Baker has a PhD in engineering economic systems and operations research from Stanford and a bachelor's from Berkeley. Her research combines OR methods and economics to decision-making under uncertainty with a focus on energy justice and energy technology research and development portfolios in the face of climate change. And with that, I'll turn it over to Dr. Baker. Thank you.
Thank you. All right, thank you very much for having me. I'm gonna start by saying I'm gonna talk for about 40 minutes on this topic here, open it up for questions, and then talk very briefly at the end about some new work on energy justice. So just to kind of give a preview. So this work is inspired by the climate crisis. We know that the IPCC in their recent work said there's a code red for humanity, meaning that we really need to act, and we need to act pretty fast. But it feels to me like deep uncertainty is somewhat impacting our ability to act and to act fast. So when I talk about uncertainty, one thing I want to make clear is that we know that humans are changing the climate and we know that we do need to act, but it's a really complex problem. And so figuring out how particular actions are going to have particular outcomes is very, very difficult. And so I'm talking about that kind of uncertainty. So what I'm presenting here is an analytical approach to support decision-making under uncertainty while leaving some flexibility and identifying some common ground. So that's what I'm going to be talking about today. Let's get this to work. Okay. So I'm talking about, so there's this word deep uncertainty, and it actually means kind of a few things. I'm talking about a particular piece of deep uncertainty, and this is when there's conflicting sources of information. And so is there a pointer at all, or does anybody know? I guess I can just point like this. So if you look up on the slide here, on the kind of upper right, that is uncertainty that comes from different types of models. These are different database models projecting costs. And so we have different models have different predictions, and different types of methods give us different predictions. On the lower left-hand side, this is when you have experts and you ask experts for their probability distributions, and we see that we get really different answers from different experts. And so those two kind of on the diagonal are really parameter uncertainty. These are kind of pieces of information that we'd like to know. You know, the cost of solar 10 years from now might be useful to know. And so we have this parameter uncertainty. But I'm also going to address model uncertainty. So down in the lower right-hand corner, I'm kind of illustrating model uncertainty. And this goes a little bit beyond parameter uncertainty and kind of reflects like different world views. And so we have all this different conflicting information. And then in climate change, we also have a bunch of stakeholders and a bunch of different decision makers. And so it just leaves a really difficult problem when you have this conflicting information, like what do we do about this? And so I'm just going to, again, just talk a little bit more about parameter uncertainty. This is not my work. This comes from a paper that came out in PNAS recently, Meng et al., just showing how different mathematical models for forecasting costs and experts, how they all kind of give us very different probability distributions. So there are all these different ways of thinking about it, and they give us different answers. And then this is illustrating model uncertainty. In particular, on the left-hand side, I'm actually going to be using this. These are 3 different functions that connect temperature change to global damages. And they come from the 3 kind of most commonly used cost-benefit integrated assessment models. And so this is beyond parameter uncertainty because they're completely different shapes, right? And the completely different shapes are, again, reflecting different worldviews. So we have these 3 different models. On the right-hand side, this just represents the technologically detailed cost, I forget, they're not cost benefit, they're cost effectiveness integrated assessment models. And again, they're just very different. They have completely different worldviews, different structures, different processes. And so model uncertainty is really even more problematic than parameter uncertainty. because it doesn't actually make sense to average models often. And so what do we do when we have this model uncertainty and yet we want to make decisions? And so that's what we're going to talk about. So first I'm going to introduce kind of the idea of decision-making under deep uncertainty. So first I'm going to talk about decision-making under uncertainty. When we have, in this case, we have kind of one, probability distribution that maybe comes from expert elicitation, and we have one model that tells us how things interact with each other. But we still have uncertainty, and so there's different frameworks. And the most common one, when people say they're doing decision-making under uncertainty, really they're doing sensitivity analysis, where you kind of look at what happens when you put different parameters in, what comes out at the end. Okay, and then you can have kind of slightly more sophisticated uncertainty analysis. You put in a probability distribution, and you get a probability distribution out at the end. So something like Monte Carlo. Okay, then down here, the kind of more sophisticated ones, you can have a one-stage decision-making under uncertainty. You have a choice. There's uncertainties. They have, different possible values. You kind of roll it back, and you can see what's your optimal decision given this uncertainty. And then, getting closer to reality, although still a quite simplified model, is dynamic decision-making under uncertainty with learning. And so you can think about you're making a decision, then there's certain things that you learn after that, and then based on what you learn, you make another decision, and there's more uncertainties in the future, and you can roll that all back and get insights about what's the optimal decision. Okay, so this is what I've done for kind of most of my career, and I can tell you it's pretty complex, actually. This dynamic decision-making under uncertainty and learning is pretty complicated just on its own. But now we have this added problem that, wait a minute, now we have a whole bunch of conflicting information. And the question is, how do you synthesize this conflicting information so you can get some kind of insights about decisions? And so that's the problem that I'm attacking. And so these are kind of the approaches, right? So this first one is the classic approach. That's where you have all these colors or different experts, so they disagree, some don't even overlap, right? They have disagreeing views. But what you do is you can average these probability distributions, and you get this one in the front, and that gives you a portable probability distribution that you can now carry around and plug into different problems. So I can take that, and I can plug it into a nice dynamic decision-making under uncertainty with learning and roll it back and say, okay, this is what you get. Given this uncertainty, this is the best decision, right? And again, this is what I've done for most of my career. It's a very, very kind of beautiful way of doing things. It's very rigorous. It's internally consistent. It's really, really nice. But in the last 5, maybe 10 years, especially around climate change, people have been criticizing it. And I have that in quotes there because that's what people have said, that it lacks external consistency. And what they're kind of getting at is the idea that we had this disagreement up at the top. You can see there's a disagreement there. And yet somehow it kind of, you roll it back and you have this optimal decision. And so people are feeling maybe not, like you're somehow missing something. So in the box below, these are my words, what I think people kind of mean by lacking external consistency, that we're mathematically resolving disagreement and plugging into a problem and ending up with a single best recommendation. Okay. There might be multiple optimal, but you have an optimal set. So that to me is, I think that's actually a not invalid kind of argument, that we have this disagreement, but we somehow are mathematically resolving it. So then there's a bunch of approaches that try to address this. In economics, they tend to be called ambiguity aversion methods. In operations research, they're kind of robust optimization. The kind of poster child for these are min-max decision things, where you basically, they're like worst case analysis. There's a lot of really sophisticated ways of doing this, but that's kind of the typical one. So in this case, you're synthesizing this disagreement, but in the context of a specific problem. Okay, so in min-max, you're gonna be using different probability distributions depending on what your actual problem is. And so I'm not a big fan, I'll tell you. I have a bias against these types of methods. Because they're lacking internal consistency, which, as kind of having a math background, that just bothers me. Among other things, if they use probability at all, they require a crisp distinction between objective probabilities and subjective probabilities, which is something that I would argue there's not a crisp distinction between those things. They also are lacking dynamic consistency. And I think, ironically, they mathematically resolve the disagreement and end up with a single best solution. So they actually, to me, don't seem to be addressing the external, the kind of external inconsistency. And so then finally, then there's another set of approaches to this. And what I'm going to introduce is actually complementary to these approaches. So the most well-known one is robust decision-making. It's kind of Rob Lempert's approach, and Klaus Keller is kind of in this group as well. So in this approach, you synthesize the conflicting information, not just in the context of a problem, but you actually synthesize it with decision makers. You iterate with decision makers. Okay, and so the typical way, and it's a general method. Let's see, I always have to look it up. They're called exploratory bottom-up methods. And what they kind of do is that they evaluate a small number of alternatives kind of against the universe of possible information. And then they iterate with decision makers to understand where the decision makers would like to be. They come up with new alternatives and so on. So what I'm going to introduce is actually complementary with this, in that we are going to identify a small set of alternatives that are, in some sense, good alternatives to be thinking about. And so what I'm going to introduce is consistent with this one. Okay, and so now I'm going to introduce the approach, and this is from a paper with Valentina Bozzetti and Ati Salo. So we call it robust portfolio decision analysis, and these are the three key aspects of this methodology. So the first one is that when it comes to kind of complex problems like climate change, we really want to think about portfolios of alternatives rather than kind of thinking of individual alternatives at once. Really, climate change is going to be solved by doing a whole bunch of things at once. Now, in my example, I'm going to focus on a pretty traditional portfolio, which is technology, research, and development portfolios. And so we can invest in a bunch of different technologies all at once. But, we would like to apply it kind of more broadly, where you have a portfolio that includes questions about research and development, questions about subsidies, maybe what your goal should be, and then maybe how you're going to get to that goal. Are you going to use a tax, cap and trade, regulation, right? So you can have these portfolios. But the idea is we start with a portfolio of alternatives. You're making a bunch of decisions all at once. Then, instead of coming up with an optimal, we end up with a set of, here I have good alternatives. You'll see in a minute, really, they're the alternatives that are not bad. So we're going to end up with a set of alternatives that are not bad. Then we go one step further and we look at all those alternatives that are not bad, and we identify individual projects or alternatives that are interesting. And so this is kind of our approach. And that last piece, by identifying these projects that are common, it kind of identifies some common ground, which in a difficult situation like climate change can sometimes help to catalyze this discussion. Okay, so to do this, we have a concept which we call belief dominance. Now, this is actually a concept that's been in the literature for a very, very long time under a bunch of different names. So I have them on the bottom there: admissibility, Knightian decision-making, objective rationality, unambiguous preferences. It's got a lot of names. It's mostly been in the theoretical literature. What we do here is that we operationalize it kind of using a decision analysis framework by really kind of distinguishing things like alternatives and preferences and information. All right, so I'm illustrating what this concept is. It's a dominance concept. It's a way to think about alternatives. So what I have here, these are three, just pretend, probability distributions, right? So let's say these are three plausible probability distributions. We have two alternatives, A and B. And so we evaluate A under this probability distribution, and U is really just an objective function. It doesn't have to be a utility function. It's just some objective function. We find the expected objective value for A, and it's better than the expected objective value for B under this first distribution. And then it's the same under the second distribution, and then it's better under the third distribution. So what we say in this case is that A dominates B, right? That B is bad, A is not bad, right? We should just throw B out because it doesn't matter which belief you have, A is better. Okay, but it doesn't leave us with a complete ordering, because you might have C and D, and there's no ordering there. C is better under the first distribution, and D is better under the third distribution. And so we don't eliminate C or D. Okay, so we end up with a set of alternatives that are interesting in some sense, or specifically a set of alternatives that are non-dominating. Okay, and so this is showing a picture, and so anybody like in economics, this will look very familiar because the concept is very similar to Pareto dominance, although it's not the same concept. But what we're showing here is, again, these are, we have probability distribution here, distribution here. Let me point out why we call it belief dominance. So we use the word belief in a Bayesian sense. So in the Bayesian framework, beliefs are probability distributions. And we actually use belief to be even a little bit more broad, and we include models in there because we think models are also kind of a belief about the way the world works. So we have two probability distributions. Each of these points here is an alternative, and we evaluate it under this alternative, and the expected value is 0.4. We evaluate it under this, and it's 0.5, right? So this is where it sits. And so all the blue ones are dominated. Each of these points, there's another point that is better under both distributions. And so we can eliminate all these dominated ones, and what we're left is with all the yellow ones on the outside. Okay, and so one thing to notice is that you can get an alternative like this, if it's not continuous, that isn't, if you drew lines, it would come below these lines, and yet it's non-dominated. And so sometimes these can be interesting alternatives as well. And then we just want to make the point that you can have probability distributions, or you can have models. We can evaluate these alternatives using different models, and again, find the non-dominated set. Okay, so I'm not going to talk a lot about this. This is for any decision theory people. It just shows kind of how belief dominance is similar and how it's different to stochastic dominance and Pareto dominance, but I'm not going to talk about it right now. You can ask the question if you're dying to know what all those meant. And then this is just showing that, that the kind of robust concepts in the literature that people talk about, they're all actually encompassed in this non-dominated set. So once you found the non-dominated set, you have the subjected expected utility. Optimal is in there. You have the Klibanoff smooth ambiguity. You have the mini-max, right? All these things that people are kind of have suggested as things to look at, they're all actually included in the non-dominated set. And so it encompasses these different ideas. Okay, so the first piece, the first kind of analytical piece is this dominance concept. And then this is the second piece where we kind of find common ground. So here, mainly look at the table over here. So what we have is we have these 6 alternatives. A, you can invest in A or not. You can do A or not, right? B, C, D, E. Each row is a portfolio. And so in the first row, we are investing in A, D, and E, and not in B, C, or F. The idea here is that these are the 6 non-dominated portfolios. And so what we do is we look for common ground, and we say, well, look at that. We invest in D in every non-dominated portfolio. It doesn't matter what belief, what the beliefs are, how you weigh the beliefs or not weigh the beliefs, you always invest in D. And so we can kind of just agree D is good. Let's all agree we're going to invest in D, and we can argue about other things, okay? And similarly, B is just not any good, right? We never invest in B, so let's throw B out. And now we're left with kind of a smaller set of things that we can negotiate about. We can maybe gather more information, right? We don't have super clear instructions about what to do, but we can find this common ground and avoid kind of mistakes, right? We kind of see that there are these common ground. Okay, so now we apply this, we go back to climate change, and we apply it to government investments in energy technology, research and development portfolios in the face of climate change. So we apply this to this is where a proof of concept to see how it would work. So on the top, I have a an influence diagram representing what this decision is. And so the square node is the alternatives. And so we are choosing between, the question is how much to invest in which technology programs. And so we have 5 technologies here. Let's see, solar PV, liquid biofuels, electricity from biomass, nuclear, and carbon capture. And then we allow for 3 levels of investment for each of these, a low, medium, or high investment in each technology. Where I'll just point out, they're not the same numbers. A high investment in solar R&D is not as high as a high investment in nuclear R&D, but they each have 3 levels of investment. Then the oval is the uncertainty. So we're not sure what this R&D investment is going to result in. It might succeed, it might not, it might succeed wonderfully. We don't really know where it's going to succeed. So we come up with probability distributions over the technology performance. And in this case, we have a cost for each of these 5 technologies and an efficiency for the 2 biofuel technologies and for carbon capture. Okay, and then this is where the deep uncertainty comes in. We have probability distributions, but there's 3 large-scale expert elicitation studies on these same technologies, all conditional on R&D. And so we take these 3 large-scale studies as our kind of 3 pieces of conflicting information. So we don't average those, we find dominance across those. Then in this case, we have a goal of achieving a 2.6 watt per meter RCP, which is very similar to 450 ppm, so just a climate goal. And then we have a integrated assessment model, GCAM, which is a technologically detailed integrated assessment model, and it chooses the implementation. So given a set of costs and efficiencies, given this goal, it'll tell us the least cost way to get to that goal. And then our ultimate objective is to minimize the cost of meeting this goal plus the cost of R&D. So that's the problem that we're solving, trying to find R&D portfolios. Okay, so I'm just jumping straight to our answer. So this is our non-dominated set. Okay, because we did simplify it, so we had 243 possible portfolios. And it's the first time we did this, so we were quite relieved that we came up with a set of 10. That seemed like a pretty reasonable number. We were a little worried that we might have 242 or something, which would not be very useful. But we have these 10 which were non-dominated. And so we have the portfolios are in rows. And so like this first portfolio, low investment in solar, mid in liquid biofuels, high in electricity from biomass, and so on. It shows this is the annual cost of each of these R&D portfolios. And then these are the objectives under the 3 large-scale studies. So 1 out of Harvard by Laura Diaz-Anadan, 1 out of FEAM by Valentina Bozzetti, and 1 out of UMass by myself. And so these are the 10 portfolios that are not bad, right? They're non-dominated. And so this is just showing how we kind of encompass these different robustness concepts. So like if you want to know the max-min solution, that's this portfolio 9. If you want to do Klibanoff smooth ambiguity for different parameters, you get some of these different portfolios. But what we think is kind of interesting and important is that there were 3 portfolios that don't obviously show up if you do weightings and different things like that, right? They're kind of uncovered. And so maybe these portfolios are also interesting. So they're non-dominated, even though they're not easy to find as a solution to any of the other types of problems you might solve. So then, so what we do now, so now we have these portfolios, and now the question is like, people have to talk about what they're going to do with them. So we don't have an answer here, but what we do is we show some ways to kind of think about it and present it. So here, these are a ternary diagram where like over here, all the weight is on the UMass elicitations. In the middle, it's 1/3, 1/3 on the 3 elicitations. And what we're showing is the portfolio that is optimal for that particular weighting. Okay, so we're going a little bit away. So, what we see is portfolio 1 is optimal if you only believe UMass. If you don't believe UMass, then portfolio 9 looks pretty good. If you think they're all about even, portfolio 2, you might be interested to see which ones have a lot of space there. So just a way of thinking about it. But, some of them aren't here, like portfolio 7 is never here. So portfolio 7 is never optimal for any weighting of these 3 beliefs, and yet it's non-dominated. So then we dig down a little bit deeper. This is similar, right? The same thing, the weightings of the 3 studies, but it's showing where portfolio 2 is either first or second ranked, and here is where it's either first, second, or third. And this is where portfolio 7, which didn't show up at all before, where it's first or second, and where it's first, second, and third. So we just thought that was kind of interesting that portfolio 7, if you're kind of first, second, or third best, it's actually kind of similar to portfolio 2. And so if portfolio 7, maybe it's got something interesting about it that isn't captured by the models, right? I mean, these are complex problems. Not everything's captured by the models. And so this kind of gives you a little bit of freedom to say, well, we're never going to be able to use nuclear power in this country or something, and so you could kind of do the ones that have less investment in nuclear or whatever, kind of things that are hard to quantify. Okay, and then we look for the common ground, and in this case, we found that there was a high investment in electricity from biomass was common, and then we never saw a low investment in nuclear. So we found like a little bit of common ground. And then we look at some, we use these ternary diagrams again to look at these individual alternatives. So nuclear, we saw it has both mid and high, but you see for almost all weightings, mid kind of dominates. And so that might tell you might be a little bit more interested in that one. And then biofuels, if you look at, just where it's optimal, then it has this kind of sliver of being optimal. But if you look at when it comes out first or second, or when it comes out first, second, or third, then it starts to look a little bit more robust, right? There's a high investment in biofuels almost always in the top 3 portfolios. So it's just a way of thinking about these things. Okay, so then we added another aspect to kind of get at this model uncertainty. So this is a very similar problem, the same alternatives, how much to invest in which technology, the same uncertainty with the 3 elicitation studies. We use GCAM again, but this time we have different types of policy. So now we're implementing a carbon tax, $125 carbon tax. We also looked at no policy or $50. And we're thinking about climate damages. And so this is where we use these 3 different damage models. So we take the temperatures and the emissions and stuff that comes out of GCAM, we plug it into these damage models to get the damages from climate change. So now we're trying to minimize the damages from climate change plus the cost of achieving the policy plus the R&D cost. So that's the problem we're solving. And so again, we have a bunch of non-dominated portfolios. And so now, we've added 3 more models that we're dominating against. And so we have more portfolios that show up in the non-dominated set, but still not too bad. So we have these 16. It's a little bit of a different problem. And so we have slightly different robust solutions. We again find a high investment in electricity from biomass is robust. And now we find that a high investment in solar is robust. And then the other 3 technologies, we see that there's, non-dominated portfolios that have kind of all different types of investments. And so now what we did here is again the same ternary diagram, what we did before, the different weightings, but we did it separately, one using the DICE model, one using Page, and one using Fund. And so what we saw here that we thought was most interesting was that for nuclear, the model uncertainty or structural uncertainty looks very important. And so how you model these damages made a difference in whether you end up with a mid investment in nuclear or a high. I don't know if anybody here knows that it was also kind of interesting because DICE you generally think of as falling in between Fund and Page. So it was kind of interesting that these results were one way and Fund and Page were another way. With CCS and biofuels, we see less structural uncertainty and a lot and pretty dominating kind of solutions in many cases to what you see, but there's still uncertainty here. I'm not going to talk about this one. There are the 3 different policies. So we looked at no policy, $50, $125 carbon tax. So what we did is we looked at the non-dominated sets for each of the 3 policies, and we noticed that there were 4 portfolios that show up in the non-dominated set of all 3 policies. So again, it's just one way to kind of narrow these down that maybe these are somewhat interesting portfolios for decision makers to think about. So again, we don't go kind of beyond this because the idea is, now I would give it to Klaus or somebody like that, and to figure out, the DOE, who the decision makers are, and really start talking about how do these different portfolios compare. Let's really think about all the various ways these portfolios can be interesting and iterate and see if we can come up with a good decision. Okay, so, yeah, actually quite ahead. So these are the conclusions for this first part, this kind of decision theory part, that it looks like deep uncertainty is important. I do think there's a role for analysis to play under deep uncertainty, right? That analysis can help us avoid mistakes, especially, right? If you don't do any analysis, it's easy to kind of get off in, a person who's very convincing can kind of convince you to go off in a certain direction. So we think analysis has a role to play, but it's also nice to kind of leave this flexibility for decision makers to kind of look a little farther rather than just having kind of here's an optimal. And then this kind of finding common ground can be useful. All right, so I am going to pause for 5 or 10 minutes for any questions that people have about this, and then I have another piece that I will go on and talk about energy justice after this. So, any questions? Okay, I think they want you to use the microphone. Yep.
Yeah, my question was, one of the things I noticed is that the nuclear recommendation really depends on the model. I was wondering if that is both the damage model and the value model you were talking about there. Just in general, what those damage models for nuclear include. Do they include sort of tail risk disasters?
So we have, the 3 corners of these 3 corners are about how successful R&D is going to be. And then you plug nuclear into GCAM, which has, so one thing we didn't do is use multiple of these type of integrated assessment models. So we only have one of those. They have kind of a worldview, and nuclear is actually, they're pretty comfortable with nuclear in GCAM, right? It tends to do pretty well. And then the damage functions from these 3 models, I think, are only climate damage functions. So I think what you're asking is there any kind of concern about nuclear itself having other damages? And I do not think, I'm not positive, but I don't think that's in any of these. So that's that I'm correct about that. Okay, yes. So that's exactly the kind of thing, right, that, because all this modeling is so complicated, so that people might want to talk about when they're thinking about investing in R&D for different technologies. So again, this is R&D. So some of the R&D is R&D to make it, at least especially to address non-proliferation, more than maybe the kind of nuclear disasters. People, when I was, or at least when I was doing it, people were very interested in kind of proliferation and non-proliferation kind of things. But that's the kind of thing that you might want to discuss, and it's not always as easily quantifiable models.
Thank you.
Can you tell us about the user community for these kinds of analyses? Who uses them? What do they do with them? And maybe some examples where they've made a difference.
Well, I mean, that's we haven't really gotten that far in. Now, the DOE definitely uses the integrated assessment model results. And they're very interested in trying to figure out how to use the expert elicitations and the uncertainty kind of results. But, trying to get this in front of people, so I don't know. But they do use integrated assessment model results. What we would like them to do is to think a little bit more sophisticated about kind of the whole range of uncertainty and looking for robust solutions rather than just solutions like that. So they use some of these pieces. The study came out of a workshop put on by the DOE, but, I personally have not had really a lot of luck in getting people to look at things again. Although partly it's because there's a few years they weren't doing climate change research at all. So I haven't really been looking at it more recently. But no, it's a good question. It's something I've been trying to figure out, like how to actually get in there and influence people.
Thank you, Erin. This is really interesting. Elizabeth Wilson, Environmental Studies. When I was on detail at DOE, I appreciated that oftentimes the models were used to justify their specific program. And when CCS, for example, didn't look very good, the modeler was sent back to the office to change the numbers and make it look good. And so I appreciate that oftentimes these models are used to justify specific political realities. And within DOE, there's a lot of sharp elbows and fighting, and it isn't an optimized or even a decision under uncertainty, but a political battle for resources. And I'm just wondering how you think this type of work would interact with that very political scenario that involves, legislators' districts and kind of embedded energy infrastructures and kind of our very politicized decision of energy decision-making within this country.
So, again, I don't know. It depends how much they put any weight on analysis, but the idea is to at least try to eliminate the things that don't make very much sense, right? So that's what the hope is that you're like, yeah, well, all we can do is provide the analysis. If nobody pays attention to analysis, there's really not much we can do. But, at least if you can kind of, and this does give flexibility, which I think people like better, having some flexibility. We're like, here's the set of things that are not bad. So we hope having a set of things that are not bad, they will avoid the things that are bad. But, I don't know. That's definitely I'm the analyst. I'm definitely not the one who understands the political decision-making process. So. Any other questions? Okay, then I will like to go on and do a fairly brief piece talking about carbon capture and environmental justice. So this is totally work in progress right now. It's out of a program we have called the Elevate program, which is focused on energy equity and climate resilience. And it's all about kind of convergence research. And so this is with Paula Furlanetto. So she's a student of mine in industrial engineering, but she has a background in electrical engineering. And then Bridget Diana and Michael Ash, who are economists. And so we're looking at carbon capture. So just quickly, in case people aren't familiar with carbon capture, basically it's the idea is you have a power plant and you capture the carbon at that power plant. And then you can either use it or you can put it in a hole in the ground and store it. But you get it out of the air. So carbon capture. And so some people are interested in this technology for climate change, right? It means you can continue to use fossil plants and but not let the carbon out into the atmosphere. But environmental justice communities are very unhappy and very suspicious about carbon capture because it allows you to continue using your fossil plants and, just solve climate change, but it doesn't solve the problem of local pollution. And so environmental justice communities are low-income communities and communities of color who are disproportionately exposed to pollution from many different types of facilities, including generation facilities. And so they're like, they don't like the idea of just like sticking carbon capture on and leaving the polluting plant there. And so we wanted to look into this. We've actually found there's kind of this sense out there, but we really haven't found very many analyses of it, and including especially kind of a systems-based analysis. So what I'm presenting today is a very simple systems-based analysis. So we use a direct current optimal power flow model with just 3 nodes. Okay, so each one of these bars is a node. At each node, there's a generator. And so we have a coal generator, we have a natural gas generator, and then we have a wind generator down here. And then at these 2 nodes, there's a load, there's demand, there's population, and they're demanding some electricity, and they're demanding electricity. And then we have transmission between the different nodes. And this is a very simple symmetric model, but it gets at kind of some of the complexity that you see in real life. We just made up, this is actually just a completely made up wind, how the wind is blowing, right? So sometimes you can generate wind energy, sometimes you can't. And then what we are interested in is looking at climate policy, carbon policy. And so we look at this when there's no limit, when you are trying to be at 64% or below, or 32% or below. And what we want to think about is what happens to local pollution in those cases. Okay, and so these are our initial results. So these are local emissions. In fact, this is specifically just one kind of local emissions, NOx, right? We're just using it as a way to think about local emissions. And you have to note that local emissions like NOx don't act the same way as CO2 when you have carbon capture. okay? Because you're capturing the carbon, you're still getting the other emissions. So we're measuring how much NOx here. We are taking the amount of wind just as given. So we're just saying, like, you've got 400 megawatts of wind. And then we're looking at the 3 policies. So in each case, the first bar is there's no limit on CO2. The second one is this mild policy. And the third one is the strong policy. And then if there's stripes, that means that you have carbon capture with that generator. So we have, it's very simple. We've got a fixed demand. We do have like constraints on turning power plants on and off and that kind of thing. The plants already exist, but the model chooses to build carbon capture and then it chooses where and when to generate power. And so we found in this, simple problem, we found 2 kind of interesting results. So the first one is this, that as the climate policy gets stronger, you end up with more local pollution and sometimes with a lot more local pollution. And so what's happening is that coal is way more polluting for NOx especially than gas. And we parameterize this using fairly recent prices, which you will see is not true in a lot of models. So natural gas is cheaper than coal in this case, right? Because of fracking, natural gas is actually cheaper than coal. In a lot of cases. So we're using our natural gas, in the basic case, we're using all the natural gas we can, and then coal is filling in the rest of the power. And so in this case, we add carbon capture to the coal, and that does pretty well, and it only adds a little bit of extra generation. But in this case, when it's very strong, we add carbon capture to both natural gas and to coal. Because natural gas is generating so much energy, there's a big energy penalty. You have to produce a lot more. It's being produced now by coal. We get a lot more local emissions. Okay, so it underlines the part that these environmental justice communities aren't being ridiculous at all, that you can end up with a lot more pollution under a carbon policy than without. And then the other interesting one is as you add wind, again, we find even more local pollution, at least for a small amount of wind. This is because once you add wind, it's no longer economic to add carbon capture to the gas generator, but therefore to meet your emissions cap, you generate less with gas and more with coal. And so in this case, we end up with even more emissions, and then it does finally go down. Okay, so these are just very, it's kind of made up parameterization, but just to get a sense of what's going on and how it is a systems problem. And so what we're going to do is we're going to parameterize these with some real live cases. So our collaborators, Michael Ash and Bridget Diana, did a project called Green for All, where they just looked at carbon policy without any carbon capture. And so they found some kind of interesting cases. So here is a coal plant in a very rural area. Here is a natural gas plant in a very urban area. And that's not uncommon. Coal often is more rural, gas is more urban. And they just have there's more low-income people near the coal plant, there's more people of color near the gas plant, but there's just plain old lots more people near the gas plant. So they found that under a kind of a mild carbon policy, that generation moves from the coal plant to the gas plant. And so sometimes it really causes a problem for more people are being exposed to pollution, and often more low income and more minorities are being exposed to pollution because of that. So we haven't done it, but ours might, interestingly, by putting the carbon capture on the coal plant, might actually move some of the generation, back up to the coal plant. So you'll be doing worse in this small rural area, but you'll be moving pollution away from the large populations. We haven't run it yet, but that's kind of our hypothesis. And in particular, there's all different kinds of cases, right? And so we want to kind of get a sense of where would carbon capture make things worse? Where might it make things better? How can policy intervene in that? And how can technologies intervene by because there are different possible kinds of carbon capture that can actually capture local pollution. And so that's, this is just saying where we're going to get our data. Oh, something got lost. But this is from eGrid. We find out what comes out of the generator. from either APEEP or an in-house plume model, you figure out where those pollutions goes, and then the census will tell us what happened. So that's kind of a project that we're working on right now. And then this is just where we're going. All right, so that was just a quick kind of brief introduction, mostly just because I think it's kind of fun to figure out, like, how do you kind of get equity, and how does modeling play a role? And so it's just a problem that we're interested in. So now I'd be happy to answer questions if anyone has any questions or comments on this one. Thank you.